I will continue description of this equivalence on epidemic model, quantum tight binding model, and quantum artificial intelligence, especially in relation to quantum machine learning and quantum neural networks. So basically, I am assistant professor at Krakow University of Technology, and I'm still developing my company, Quantum Hardware Systems. And this company is oriented on integration of new emerging quantum technologies with already existing technologies, which are mostly classical. All right, so let me first remind me what was mentioned last time. So basically, we have this quantum mechanics. And in quantum mechanics, we have this issue. There is always so there's equivalence of quantum mechanics and classical statistical physics in certain regimes, I would say. Obviously, there are different theories, but still there are recognizable analogies, and I will try to exploit those analogies from mathematical point of view and from technological point of view. So it can become possible to be able that we can build a new type of a quantum computer that is more kind of stochastic quantum computer. So yeah, so basically those I need to refresh and our view on classical epidemic model. I will mention one explicit example, and then we will see the full equivalence of position-based qubit that is known as Vannier qubit with arbitrary nonlinear or linear epidemic model. So so let me first underline the issues of quantum mechanics. So there's a superposition of states as it is also in classical physics in waves, for example, among waves, electromagnetic waves. There is entanglement and non-local correlations that are very unique feature of quantum mechanics. Still, there are some people that can recognize quantum-like entanglement behavior of classical systems. So this I will touch this issue during this presentation, so I could figure out how to justify a kind of quantum entanglement in a classical epidemic model when we have two cities and there is, for example, COVID disease that propagates between those two cities. Right. So there is right. So all right. So there is some nice comment from Jarek Duda. Stochastic quantum computer sounds like Vic rotated using Boltzmann instead of Feynman path integrals. What is Eigen model, which in theory allows to solve NP in polynomial time. So thank you for a good comment. All right. So I will move on. So so we need to have we have this issue of quantum coherence, and this quantum coherence is particularly difficult in technological implementation. So like quantum dots, they usually have a quantum coherence time in the range of nanoseconds. Then it's better to use superconducting electronics as in IBM Quantum Experience or as done by Google and many other companies as D-Wave. So quantum coherence among Josephson junctions can last from microseconds to milliseconds with use of Transmon qubit that uses both electric and magnetic field for control of physical state. Yes, quite recently there are NV centers in Diamond, and in such cases, people manage to obtain quantum coherence times in the range of even seconds if the system is cooled down, or in milliseconds if NV centers are at room temperature, which is very remarkable. And well, we have this also ion traps, obviously, that is well known that can preserve. Yeah, so we have this ion traps. In ion traps, the quantum state can be stored in a seconds, but still the ion traps are not fully scalable. So the most kind of attractive feature, attractive quantum technology is about using NV centers in diamond, or about usage of Josephson junctions or single electron devices, which I am promoting. All right, and there's obviously there are some Zurich work on non-cloning and the theorem in so you cannot clone the quantum state, and there's also no deleting theorem, and yes, there's also path integral approach which applies both in quantum mechanics and in statistical physics, but is more known in case of Feynman diagrams. All right. Okay. So let me move on. So basically, classical statistical physics has some obvious features which are similar to quantum physics. So in quantum physics, you can say that you associate statistical ensemble to each particle. And usually in statistical physics, you have statistical ensemble in case for more than one particle. That's a kind of difference. So so if we have a statistical processes, yes, and especially many number of objects, yes, there is a superposition of various configurations, various states. Yeah, but rigorously speaking, this superposition only takes place in a quantum mechanics before the measurement is taken. We have also path integral approach. So you can imagine we have one boat that is drifting, and then there is point A and point B on the lake, for example, and there are some currents. So there is a probability for a boat to move on a certain trajectory, and there's infinite possible trajectory class, but still certain trajectories are more promoted, more probable. So this is this type of path integral approach, I would say. Right. So we have a stochastic determinism in both type of theories. And in both type of theories, one can say that there is a kind of intrinsic noise. This is famous statement by Landauer. Noise is information. So noise is not a trash. So we can use, with very clever design of various information processing technologies, we can use noise as ally, not as enemy. All right. And then I give short review on quantum mechanics. It's very old theory from the 20s and 30s. The main postulates of quantum mechanics has not really evolved since that time. Obviously, the mathematical apparatus was developed. And the same considerations which I'm doing can be extended further in more sophisticated way. But I want to simply underline certain concepts, so I'm using the simplest way of description. So we have equations of motion for isolated quantum state, and this is just done by Hamiltonian acting on a vector that is a quantum state on a ket and on ket psi, and then we have this change of quantum state with time, and there is imaginary minus square root of -1 times h bar, that is a Planck constant. So this is just one simple equation that has Eigen Energies that act on, and there is a quantum state here, right? So it's more practical to use wave functions. So we have this wave function description of the same equations of motion, and then we are simply dealing with a Schrodinger equation for one particle. So we have a kinetic term, potential energy term, and then the result so both kinetic and potential energy stands for a mechanical energy of a system, and that's also reflected in time evolution of a quantum state with time. So if we have representation of Hamiltonian in a matrix form, then the equations of motion can be written in such compact way. And if for various certain type of cases, we can find the analytical solutions, as it will be mentioned later. And obviously, we have a probability of finding particle somewhere in the space. So there's normalization condition, and this is obviously quasi one-dimensional description, but it can be easily generalized to 3 dimensions. So we have a probability density of finding particle at a point x, and obviously usually when we check for existence of particle, we check certain interval of positions. So there is integral from this density probability, right? So what is important is that this wave function is a complex value function, and I'm now using just scalar representation. I'm omitting the spin degrees of freedom. So basically, we have a real part of this complex value and imaginary part, and later it will be seen from my considerations that we can actually having this square of this amplitude of this probability, square root of the density of probability can be is composed from real part of a wave function and imaginary part. So formally, we can recognize two real probability and imaginary probability that adds up, and what is being observed in a real experiment is this effective PT that depends on time. All right, so and obviously there are Eigen Energies, and these Eigen Energies can be continuous and discrete. So in classical systems, we are having continuous value of energy. Here, the story is different. And it's also important to underline that usually we focus in our analysis on one isolated quantum system that is never fully isolated from external world in a real experiment. So for a not isolated quantum system, this Hermitian property is not taking place. So simply this is simply we have this in case of the dissipative systems, for example, we have this case when this Hermicity relation is not fulfilled, so there is no equality here. Dissipation is nothing else as additional part of Hamiltonian that is not well accounted by us, but has certain impact on evolution of a quantum state. So actually, this is the same. This is a bit similar in classical physics. We can also introduce dissipative terms as in case of pendulum, when there is a friction, and then simply there is, we don't fully know this dissipation, but usually we parameterize by some coefficients, like friction coefficient is a good example. Behind a friction coefficient, there is a very complicated Hamiltonian that is usually unknown to us. All right. So here, this is again, I'm just making this reference to a single electron devices. So first such type of concept was introduced by famous physicist Lee Karev. He's currently at Stony Brook. In my view, he's supposed to be one candidate for a Nobel Prize, but unfortunately, he was not nominated for such type of reward. So he initially invented rapid single quantum flux electronics that uses magnetic flux in a superconductor devices for information processing. And later he turned his research focus on semiconductor electronics, and he was one of the pioneers of single electron devices, especially in theoretical description. All right, so so here I would say I'm monitoring the news on development of quantum technologies, and I see the importance of being concentrated on one type of research, since there are a lot of news. So just today I learned that Microsoft company is promoting also development of a CMOS quantum computer that uses single electron devices. And Sydney is in association with Microsoft. It's one of research centers that makes such research in this direction. So the central idea is simple. In CMOS technology, which is very successful technology, most recent devices has 10 nanometers of a channel length. So this is distance between a source and drain. And we have naturally present a kind of semiconductor nanowire, and then there are regions of source and drain, and there are very thin insulators, and on the top of insulators people usually place the electrical metallic gates. So since so there is like company in Krakow that develops technology that already designs circuits with 3 nanometers of a channel length. So in such case, we have less than 30 atoms in one between source and drain. And in such cases, we can think about injection of very small charge to source and drain. So we can have a chain of such quantum dots that are, and the interaction between those quantum dots can be controlled by certain voltage that we applied to those gates. So we can electrostatically control this interaction between quantum dots. So you can imagine we can have a graphs of arbitrary topology, and we can switch on or switch off certain branch of graph electrostatically. So the idea is that we inject the electron to a quantum dot, and this electron, a single electron or more than one electron, is oscillating within the left and right region, and there is characteristic oscillations frequency. You can find more details in those papers that are described on the slide. So so it's a very remarkable feature that CMOS technology can be cooled down even to 100 millikelvin, and all functionality is more or less preserved. So because of high logical density and already existing technologies, it's very likely that new quantum computer or one of the examples of a quantum computer will be based on a CMOS electronics. So then theory is needed, and obviously more than theory, technology is needed, otherwise nothing can be constructed. So we have these oscillations of presence on the left and right quantum dot, and the necessary condition for those oscillations to take place is at least occupancy of 2 Eigen energy levels must be fulfilled, and this frequency of oscillation is proportional to energy difference between those 2 Eigen energies. All right, and so this is so-called Wannier position-based qubit. This is not prominent. This is less prominent direction of research. Most people those days, they do devices in a spin-based qubits. Well, still, this scheme can be converted to spin-based qubit if we inject more than one electron. But I'm still covering this approach for electrostatic position-based qubit, which I will name as Wannier qubit. So there's work of Fujisawa and Peta on that and many others. All right. So basically, how to describe such system? It turns out that if we make very strong simplification, as we just limit ourselves to a wave function on the left and on the left quantum dot, on the center of left quantum dot, and on the center of right quantum dot, basically we have transformed continuous problem into discrete problem, and this is like discrete mathematics. And then the Hamiltonian has very simple form, so it's matrix 2 by 2, which obviously has two eigenenergies and two eigenstates, and those states are AP. So this matrix has structure AP1, AP2 that gives you value of localized energy on the left and right quantum dot. So this is energy that is not this is like standing wave that is not traveling between and those two quantum dots. And then this part of energy which is traveling is associated with Hoping term. So in case of non-dissipative Wannier qubit, this we have TS1 and TS1 conjugated. So there are two complex values, but basically modulus TS12 is this part of energy that is being transported from left to right quantum dot. And this is a cyclic process. So this action of this Hamiltonian on the quantum state results in dynamics of a quantum system, so change of wave function with time in according to this scheme. And this is obviously reflected in energy of a system, in eigenenergies of a system. All right, so that's very simple philosophy. And then you can ask yourself how to relate this simple quantum tight binding model to Schrodinger equations. Well, the prescription is that basically in case of two coupled quantum dots, we can categorize this the existence of wave function with two maximum localized wave functions on the left and right quantum dot. So basically there is a linear combination of, so in every time instant there's the wave function which is being observed is a linear combination of a two Wannier maximum localized wave functions, VL and VR, and yes, so you can extract those wave functions, maximum localized functions, just by solving Schrodinger equation, which will be shown on the next slide. So this prescription for AP1 and AP2 coefficients is given here. It's such integral, and we have this kinetic and potential energy term here in both cases, but so we can see here, but in this particular just on the very bottom part we have VR, VL, or reversely. So this is Hoping term, which can be seen here. All right, so let me move on. So basically, under different circumstances of polarizing, so there are different configurations of gates that control the connectivity between quantum dots. You have basically three voltages that you can apply to a single qubit. So these three voltages generate different effective potential, and these different effective potentials, one can see different wave functions. So it's also possible to have a conversion from position-based qubit to a eigenenergy-based qubit, which is dominantly used. This was done in this SPI paper, which I mentioned before. And the process of such conversion is described here, but I am not going to discuss it in details since it's not the main issue of this talk. So yeah, this computations have been done with Toeplitz matrix approach, which is very simple approach. All right. So let me move on and have some further reference to this epidemic model. So my first considerations with analytical structure of solutions were done in this cryogenics work, and also analytical view on two coupled single electron lines. So here is again the same concept shown. You see, you can control. You can have also entanglement between those two qubits. Simply, electrons will interact in by means of Coulomb force or electrostatic energy in more formal way, you can say, and there will be emergence of a quantum entanglement. So actually, it will turn out that the ground state of a system of two interacting electrons, I would say two weakly interacting electrons, the ground state will compose the anticorrelation. So two electrons usually will tend to be at maximum distance, but still there's some level of correlation. So yeah, so this is a quite unique feature of a quantum picture, that this correlation and anticorrelation is present in such quantum system at a ground state. In classical ground state, you have only anticorrelation. All right, and this case of those two interacting Wannier qubits, electrostatic interacting Wannier qubits, will be covered by a matrix 4x4, which is the most minimalistic. Obviously, you can, for the sake of further quantum information processing, you can place the whole system to external source of microwave field. This is like dipole antenna, and you can induce another transitions between Eigen Energies of a system, and also you can implement the quantum communication, which I'm not going to mention here, but basically it's possible to have entanglement between a radiation and matter and radiation and those two electrostatic qubits. All right. So this anticorrelation principle is very intuitive, I would say. If you have two boxes that have charge balls, those charge balls will tend to be at maximum distance. That's the way for a physical system to approach the ground state. So this is naturally, I would say, this system is naturally a logical inverter, and still the system of it's logical inverter. You can implement both classical and quantum electronics using the concept of charge balls. Simply, one electron is such charge ball, but it will be distributed in a continuous wave due to solutions of a Schrodinger equation. So so this is a classical quantum inverter, and you can move on further with your considerations. You can have an inverter that is additionally controlled by external controlling bit or qubit, as you like, and so this is a Synod Gate, which is given here, and it's being described in the SPY paper. So yeah, also so it can this gate can be described both by Schrodinger equation or tight binding model. Okay, obviously you can think about arbitrary more any. So you can design as complicated quantum gates as you like using the same concept. All right. So there is also a case of a quantum neural network. So so this particular solution was proposed by me. So you can have a chain of coupled quantum dots, and you can place the red lines are this quantum dots, and this which are interlinked. There's electrodes that control the connectivity between two neighboring quantum dots. So you have various controlling signals. So essentially, you can inject free electrons, and you can make information processing with having very specific dependence of voltages applied to this controlling electrodes, I would say. So it's kind of complicated task to optimize this neural network for certain information processing purposes. Basically, at least in accordance to this picture, we are dealing with three quantum bodies. Like every electron is a quantum body, and once injected, it will be present everywhere. So it starts to be bit complicated. problem of n-body problem. So more you have injected electrons, more complicated problem it is. And you can have layers, and you can also use a magnetic field for control of the system. So you can use both electric and magnetic field. You can also, in the shortest version of this neural network, you can, in the spirit of this analytical view on the single electron lines, you can disconnect them and just let them only to interact electrostatically. And this is also possible. So yeah, such scheme of quantum neural network is also possible. All right, so you can find some of this description in this YouTube, which was presented some time ago. All right, so what's the philosophy of interaction of two Wannier-based qubits, in an electrostatic way? Well, again, we have a system of two single electron lines. So we have a source and drain for each line, and there are 3 electrodes that control the physical state of this qubit, and also 3 electrodes that control the state of this qubit. In addition, you can also apply source of vector potential. You can apply external solenoid if you like, but I will omit this issue right now. So such system, in the most basic approach, most minimalistic approach, is described by 4x4 Hamiltonian. This is the structure of this Hamiltonian is given. So we have a hoping between. So we assume that this electron is present on node 1 and 2, and it's not tunneling. Still, tunneling processes can be accounted, but let's say in first approximation, they're omitted. There is also possibility of a tunneling externally, and this will be called this will be rated with dissipation, which I am going to mention. So there's dissipation that is due to tunneling process. So then electron escapes, and then the normalization of wave function is no longer preserved. So simply the harmonicity of matrix is no longer existent. So this tunneling actually can be obtained by these diagonal terms AP1, AP1B, and so on, to take complex values, not real values. But so far, in case of isolated quantum system, we have all these diagonal terms that are real value. And here are hoping terms. So the electron can naturally move between 1 and 2, or 1' and 2'. So you have this some of diagonal terms that are non-zero are due to hoping, and they can have a complex value, especially if the system is placed in external magnetic field. So there's this degree of freedom. There is a Coulomb force, or Coulomb electrostatic energy. This is between, essentially, the situation here are simplified. So we have interaction of 1, 1', 1, 2', and 2, 1', and 2, 2'. The particle is not self-interacting, so there is no. So there are 4 channels of Coulomb interaction in this simplistic model. But this simplicity has the central value, and the central value is analyticity of solutions. So this Hamiltonian acting on eigenstate, that is written in such a way as square root of probabilities times phase factor. So this P1 is a probability that particle in upper line is at 1, and a particle on another line is at 1'. Then P2 is a probability that a particle at first line is at 1, and second line is at 2', and P3 is probability of finding first particle here and another particle here, and fourth is both particles that are at 2 and 2'. Yeah, details are given here. All right. So this was so far the short introduction to tie-binding model. This is a slightly different case of tie-binding model that is mostly known in literature. And basically, yes, this is epidemic model. It's a very simple story. We have a matrix that acts on this probabilities, and the result of this action is change of probabilities with time. There's also nonlinear. So this is case of linear epidemic model. The nonlinear epidemic model will be mentioned later. This is upgrade from last presentation. in nonlinear epidemic model, this S11 coefficient will depend on P1 and P2, and so on, and S12, S21, and S22. So, but then the purpose and the intuition is simple. Epidemic model can you describe your stochastic finite state machine for sure, and basically, if you want things deeper, all these single electron devices also can be regarded as stochastic finite state machine, since evolution of a quantum state has stochastic feature, right? It's a stochastic determinism. But then, yes. So this is not very well known. I'm still working on this issue. Details are on archive paper. So the result of this action of this matrix can also
Chris, can I ask a question during your presentation?
Yes, go ahead.
You mentioned a term that kind of is raising a red flag of my increased interest, that is the stochastic finite state machine.
Mm-hmm.
In the stochastic modeling that I'm familiar with, usually the finite state stochastic systems, sort of a beginning of it is done via the Markov of semi-Markov or hidden Markov models. Relationship between what you call stochastic finite state machine with this type of models?
Yes, I will underline this relation farther on. So I will simply, on further slides of my presentation, this matrix S will be translated to Hamiltonian, and I believe that yes, you can construct like cumulant generating functions from behavior of many single electron devices. I'm thinking in such type of direction, but I did not yet approach. I still need to arrive to a new type of solution. So give me some chance to to mention about this later. But
when you are working on finding a solution of such system of equations, and if you know Markovian property or some slight generalizations of Markovian property. Markovian property is essentially a lack of memory. That is, the transition from the next state depends only on the previous state and the conditional probability. So when you have this type of property, then it's significantly easier to find a solution of such system, and then the simulation of real life situations will become more feasible. You can reduce the complexity to just few parameters.
Yeah, but the thing is that yes, I can approach if I introduce some external noise, or if I introduce some very strong dissipative factors in my quantum model, I can approach a kind of the case when the memory is less and less of last events is less and less important. Yes, I can do this. So this can be partly reflected in the models that are being described. But obviously, the case of complete lack of memory, well, yes, I have one type of thing but maybe in some time I will refer to. But I would say I see value in memory actually for information processing. So it's not completely. So I might approach this case of lack of memory if I have very strong dissipation.
Markov property doesn't mean a complete lack of memory. It means a sort of a quick disappearance of memory. That the memory is sort of can be controlled. It's if you have some probabilities of large case dependence, and they will be vanishing to zero pretty rapidly, with the exponential rate. So
yes,
it's not a complete lack of memory, but Markov property enables you to write down equations of dynamics. Those are known in stochastic, traditional stochastic modeling as Chapman-Kolmogorov equations.
Yeah, but the thing is, there's no deleting theorem in quantum mechanics. No deleting theorem, which says that you need to consider certain memory. Yeah, but anyhow, with external disturbances introduced this system, we can approach this situation when we have less and less importance of less and less dependence on previous history, right? Yeah. All right. So thanks for the comments.
A very simple discrete time model that emulates the Markov property is the autoregression order 1 model, where the current state depends linearly on the previous state plus some independent error. So after a couple of steps of dynamics of the system, you have some memory, but the memory is quickly disappearing with the exponential rate.
Yeah, so I would say I make a presentation on about non-invasive measurement of charged particles by single electron devices. So this situation will be presented at the workshop organized by you. So in such cases, with many particles passing in a proximity to a qubit, yes, this its state can be strongly affected, so it is less and less dependent on previous history, right?
Okay, yeah. Sorry for the interruption.
I will try to address this issue on this presentation. Sure, welcome. All right, so the thing is that obviously there is presence of presence of matrix acting on vector, so we have eigen states and eigen energies, but we only have positive values of probabilities. So usually we have a mixture of two levels present in such type of model. So, but when we want to move to quantum case, we feel intuitively that in a Schrodinger equation we have a square root of probability. So we need to convert it. So the very simple algebraic observation is this one, and then yes, and then we make steps. So so in direct comparison, tight binding model is about action of this matrix on such a quantum state, as given here. So so that's quite simple, right? All right, so so this is just a simple algebra, but then you can see that the problematic term is due to existence of phase, but this can be rewritten to be present. So basically, what you can see is that this model is one model can. So this tight binding model converted to epidemic model brings you the presence of phase in this on these diagonal terms. I will describe this process step by step later. All right, so basically there is a chain of so that's how it is. So here we move from this yes, so now I'm moving from tight binding to epidemic model. So we have such equation. One second. Yeah, we have such type of equation, and basically we so we have a square root of probabilities, and then we need to convert to the situation where we have a P1 and P2 here, and its derivatives. So so basically what we are doing is we are applying such type of matrices on both sides, and so this expression is equivalent to this expression. So so we see that on the right side here we have P1 and P2. So we have multiplied two sides by so first by this theta and secondly by this diagonal matrix. So the details of that are present in this archive paper. This is unfortunately is a bit lengthy paper. So so basically so finally the prescription is that so having the parameters of a tight binding model, we get S matrix parameters. So basically our S matrix is this guy. So this term, this matrix, and this matrix. So 1, 2, 3, 4 just stand for S matrix derived from tight binding model. All right, and then there's an issue how to introduce this dissipation to this model. So first intuitive thing is that you place complex values for localized energy for left and right quantum dot. So if you force the whole quantum state to be only on one quantum dot, then you have AP2 set to 0, and you have 0 Hoping constant, but still there is a probability for a particle to escape outside, and this is this imaginary term. Here, this analogy is very strong with resonant cavities. You take a Jackson book on electromagnetism, on electrodynamics, and there, in the theory of cavities, you have so-called the concept of complex value eigenfrequency of a cavity. So given a cavity can store you like resonator, there's some dissipation in this resonator, and this dissipation can be reflected by imaginary part of its eigenfrequency. So this issue is already well covered by classical physics. So this is, so it's not surprising that we can apply here the concept of dissipation. And so AP1 and AP2 are complex valued, and still the Hoping constant TS1 and TS21, they don't need to be Hermitian. They don't need to be they don't need to have the same modulus basically. And yeah, so this is how you but still the dissipative model can be fully solved in case of analytically. It's described by matrix 2 by 2. It's just a small nice exercise. All right, so we know what's the meaning of those dissipative terms, and now so far I make a first approach when I just describe you how to move from tight binding to epidemic model, but there were some problems with presence of phase. Another way of doing such thing is simply by using the concept of real and imaginary probabilities. So we have a wave function at given time instant has real component and imaginary component. And if you let us just concentrate on a single position-based qubit. So in such type of case, we have we can write its state in such a way. So it is for two quantum dots are related to at least to four-dimensional vector, and this vector has only real values, and then there is a Hamiltonian which acts on a such system, and it turns out that the set of equations can be fully equivalent. So the previous version of a tight binding model, which was simply this equation 5, is fully equivalent to the equation which I'm considering here. But here we don't have imaginary factor, and then you see that also dissipation is taken into account, and then in such case we don't lose any type of information. So basically, you can sense from the way how it's written that minimalistic tight binding model of a Wannier qubit is equivalent to stochastic finite state machine that has 4 states. And there are 4 states that will be specified here. All right, so so doing some algebra with this expression, so you have to multiply so you approach to this one expression. So so you need to make some tricks to convert this previous structure to epidemic model, because you have here a square root of probabilities. Tricks are very simple. This is like identity matrix. You see those 2 matrices stands for identity, but this term will hit this guy and they become not a square root, but just values p1 ri, p2 ri. And the right side will also become of such shape. And then, so your S matrix acting on probabilities is equal to time derivative with respect to these probabilities. So your new S matrix is nothing else as this the multiplication of these 4 matrices, right? So this is a very simple story, and the process is, so you see there is mathematical equivalence. All right, so so we end up in such type of S matrix that relates to a tight binding model. So it's very good because this is a prescription. So if you want, you can come to me and say, please design me such a system, such stochastic finite state machine that has such is described by such epidemic model as with parameters as I give you, and then I can convert you this epidemic model to a quantum type binding model, and then I can simply design a quantum technology, quantum circuit that simulates this classical stochastic finite state machine. So actually, when you look on this equation, turns out that it has very simple, relatively simple analytical solutions. So this is the state of this state is described as exponent of such matrix with integral of such matrix. So if you see these things more carefully, this integral operator will move to all terms, can be moved internally. So you have to integrate all the terms. So this is an evolution of such system with time. So you can go both ways, from classical state to quantum, or from quantum to a classical. And yeah, all right. I will move on so I can generalize, obtain results even further. So now initially I was considering only linear epidemic model, and you can say to me, oh, that's not real life. In real life we have all right. So in real life we have nonlinearities. Sure, there can be incorporated. So this is the model. So now all coefficients S11, S21, 21, and 22 are arbitrary functions of P1 and P2. And yeah, so there is a matrix acting on a state, and this gives you change with time in such a way as given by equation 15. And again, the same trick can be used to have a matrix evolution, have evolution of such system with time. Right. So, all right. So, all right. So, okay. So this is, I think this is well understandable. This is just very simple theory. All right. So now, how to move from epidemic model to tight binding model for the case of nonlinear case. So basically, you need to make these tricks, which I already exercised before. So I can rewrite the previous equation in such a way. So here we have a P1, but still there is emergence of phase, as you see, but this phase is compensated. And the right side is also written in such a way. And now And now I make a step further. So I need to get rid of this P1 and P2. So this so I multiply two sides, and I need to recover phase presence. So I multiply both sides. So I get such expression as given here. Again, it's simple algebra. So I'm having such, basically, this is my candidate for Hamiltonian acting on a quantum state. And this is a quantum state change with time, but not completely, because I don't have fully derivative. Derivative is only present here. So in order to have a full derivative in front of this, I have to add additional matrix to this evolution. This is what I'm doing. So basically, it turns out that this bracket and this bracket stands for a Hamiltonian that is obtained from arbitrary structure of S matrix. So S11, S12, S21, and S22. So and then this leads me. So this acts on a quantum state, and this leads me to a change of quantum state. The only problem that is here is that suddenly I have two phase factors that can be chosen arbitrarily. Yes, it can be chosen arbitrarily, and but still they can be accounted. They can be accounted, and it's important to underline that we can control this single electron qubit by external source of vector potential as solenoid. So yeah, this can be done. All right, so this was this exercise. I hope that I convince you that in every case I can move from, almost in every case I can move from a linear epidemic model to a tight binding model. I just want to refer to a specific example. Yeah, so this is one of the conclusions. The position-based qubit with external source of vector potential can fully reproduce the behavior of linear and nonlinear epidemic model. And that's why I called about equivalence. And there was some remarks from before. So can you attack real epidemic models? Yes, for example, SIR model, I can treat as nonlinear model, epidemic model. Our equations of motion are described by such matrix. And obviously this is nonlinear matrix that is covered by such assumptions as have been done. So this, yes, so this is still a work in progress.